Back here with another video. Today we'll be solving a problem called minimum path cost in a grid. So let's start it. You're given a zero indexed M and integer matrix grid consisting of okay. So the choices is you can move to any spot on the um row below it. Each possible okay. Oh, okay. So let's see here. 5, 14, 2. Okay. So it's basically the problem is you start from the top, anywhere in the top, and then you can choose whether to go down, right, to the next index, right? And then each grid spot, like grid I and J, has a number. So for example, 5. That's where you can locate how much it would cost from the move cost grid. And then for here, if you want to go to the first spot in the grid, you gotta pay 14. If you want to go to the next one, you gotta pay 3, and so on. So, hmm, 50. Yep, equals 8. Wait, why is it adding 6? Hmm. Are we supposed to do pair or something? Because this is a little confusing. So you're adding 6. Okay, I get it. You're adding the values you go through, and you're also adding. So I guess this is a pair problem. Wait, I guess this is not, because you can just add it to the current sum, right? So here, first of all, it would return 8, but you can just make it 9, right? Add 0 here. This would return 12, but you can return add 5 into it, so that way it turns 17. Okay, I think this is straightforward. Okay, let's just straight jump into the coding part. First, let's create a. We're doing this in memoization. Create a function that returns an int. Let's get cost. And then, do we really have to. Do we really have to keep track of the current column? I guess. I mean, but the thing is, that's just gonna be more steps for us later on, right? Oh wait, actually, we do, because if you don't keep track of the current row, that means suppose you start from here, right? You go here, and then if we call the recursion again, it could be any of these, right? any of these two. But we're calling this one, so we gotta keep track of the current row and column. So let's do int I, int j, or yeah, int I, int j. And if I is greater or equals great dot length, don't need to worry about j. Return. Oh, but the thing is, how do I say this? If we do this, okay, this is return 0, but we don't need to, right? Okay, so what I'm guessing is if it's greater or equals, or we can just do equals. Let's just do this. Grid dot length -1. We're just gonna return grid at I and j. And then okay. Yeah, we're just gonna return that, right? So let's now want to get the minimum. Now this is the fun part, the recursion cause. We want to loop through every column in the array, or yeah, every column in the array. Understand. Good. At I, the length, r plus plus, right? And if let's do int cur equals 0. No, cur equals f of grid move cost r plus 1 r plus move cost at grid at I and j. Wait. Okay, so here move cost at we're getting okay, so this is hard. So first of all, we want to get the move cost at I, grid 9j, and then here we would say R, right? Because we want to only sum up the direction we're going to. So if we're going left here, this would be 9, as so. And then we want to do plus grid at I and j, because we don't want to miss that out. It needs to be included. And then we will do min equals math.min between min and cur, return min, and then return f of grid, move, yeah, grid, move cost, and then 0, and, but we can start from, any direction. So let's do this again. And integer value. Int I equals 0, I is less than 0. And plus plus. Contain as or f grid, move cost to and I. And at the end, we want to return this. Hopefully, this should work. Okay, nice. Let's run some couple more test cases. Nice. And then the constraints are 50. I don't know how I'm feeling about that though. Let's just try submitting it. Yep, time limit exceeded. But we can memorize it. Ah, this is bad. Didn't even pass half of the test case. Ooh. Whoa. Whoa. What? That's pretty long though. Okay. Integer dp equals new integer sure grid dot lanes grid at 0 lanes if grid ij not equal to null return grid at ing grid at ing equal to okay, let's run it. I mean, EP. Nice. So now, if we try submitting it, bam. This problem was okay. It wasn't that bad. I know this is kind of like easy because the constraints are small, but the test cases were quite surprisingly long. So I think that's all. It was a great problem. A good practice for my dynamic programming series. So yeah, I think I'll see you guys in the next video. Peace.